previous lecture, we studied Lie groups and the Lie algebra that is associated with the Lie group. Now, in the next lecture, not today, but in the next lecture, we'll go the opposite way. We'll start with a Lie algebra. We want to study which Lie groups and which part of a Lie group we can actually go back to starting from the algebra, so how to reconstruct the group from the algebra. Now, today, however, we'll remain on the Lie algebra level and ask a question that's quite independent of the question where the Lie algebra comes from. We'll study a classification of all Lie algebras, and that's possible, but it's particularly simple if we study complex Lie algebras. So if we require that the Lie algebra we study consists, as always, of a vector space and a Lie bracket, which you may now take as an abstract Lie bracket, but this L is a complex vector space. Now, of course, such complex Lie algebras can be generated, for instance, from a complex Lie group. So, example, if G is a complex Lie group, which simply means that the underlying smooth manifold G is a complex manifold as we defined it when we studied various transition conditions between charts, and you may remember that for a complex manifold the transition functions didn't only have to be smooth, they had to satisfy the Cauchy-Riemann equations. Anyway, we're going to consider complex Lie algebras in this sense today, and the key theorem that brings about the promised classification is by Levy. Well, today I'm not going to prove very much, so I will give you several results without proof, but I will be conceptually clean in presenting the entire construction of this classification and the theorems that link together the various constructive elements. And that's, of course, important for applications. So the theorem we want to work towards is that every finite dimensional Lie algebra, well, we said complex Lie algebra consisting of a complex vector space L, some abstract Lie bracket can be decomposed as, so the L can be written as a Lie subalgebra R, a direct sum, Lie algebra L1, direct sum, plus a finite number of such L's. Now, this be great. In fact, it's a little bit more complicated. These here are direct sums, and I'll say something about this in a second. And this is a so-called semi-direct sum, and I'll have to explain this. Now, if you have so I'll explain what R and the L's are. Where? A. So let's start with R, and also what these direct sums and semi-direct sums are, because on the level of a vector space, you know what the direct sum is. The direct sum is simply a Cartesian product to which you inherit the addition, the addition, so the vector space operations on the various vector spaces component-wise. We had this. But now we're not dealing with a mere vector space. The vector space is equipped with more structure, namely a Lie bracket. And then this is a direct sum between Lie algebras. And therefore, we'll have to have a compatibility condition also for this bracket. And I'll provide this for the semi-direct, for the direct product here. And the semi-direct product also, or particularly the semi-direct product, has a different compatibility condition with respect to this bracket. So I'll explain all of this in a second. So what are these R L1 to Ln? So this R is a Lie subalgebra of L, and it has this particular property that it is solvable, and the solvability condition is the following. So you consider the bracket of R with R. Now this is of course supposed to indicate the set of all R1, R2 commutator, where R1 and R2 both come from R. So if I put the set in the brackets, I mean this object. So you can look at this, but you could also look at the commutator where you feed into each slot the commutator, this set. Now, this set here will always contain that set over there. And now you can continue this sequence. You can now again write down a commutator, and you feed into each of the slots. You feed this entire set here. You feed it into this slot, and you feed the same set into that slot. And that again will be such that the result is contained in this set, and so on. And the crucial question is, will this sequence ever terminate? And it can only terminate if at some point this is just a vector space that contains only the zero. If and only if it does terminate like this, then we call R a solvable algebra. Okay? So that's the first bit. R is solvable. So you can always decompose a finite dimensional complex Lie algebra into a solvable bit with a direct sum. I'm going to explain what that means, and such a bit. So what is this bit? It's B. The L1 to Ln are so-called simple Lie algebras. So I said here that R is a Lie subalgebra of L. That's true, but actually in order to state the theorem, we only need to know that R is a Lie algebra in its own right, which of course a subalgebra is. And so the L1 to Ln are simple Lie algebras. Now what does that mean? That is, by definition, a Lie algebra is simple if I pick out an arbitrary one, if Li is non-abelian, right? And L1 or Li contains no non-trivial ideals. Now, what is an ideal? An ideal is a subset of an algebra such that if you take the commutator of any element from the ideal, so again use this notation where I take the freedom to insert an entire set here, meaning take any element from the set here. An ideal is a subset where, well, it's not only a subset, it's a subvector space. Subvector space. So where if I calculate the bracket between any element of the subvector space and the entire vector space, the result will, however, lie again in the subvector space. So in a sense, the I elements, they are so strong, even if you bracket them with an element from outside, you remain inside the I. That's an ideal. All right? And the non-trivial ideal, well, I explained to you what a trivial ideal is. It's obvious that this set and the entire set are always sub-vector spaces of the entire set, trivially. And equally, it follows that whether you take the 0 or you take the L, so let's do it for the 0, and you bracket it with any element in L, of course, you will always get the 0. So now you can, yeah, okay. And equally, if you take the entire L, then you just land here. So that means these two guys are always ideals, right? They're always ideals, and hence it wouldn't make any sense to require that L or Li here, well, so a Lie algebra is, yeah, Li. It wouldn't require, let's put an I here everywhere. It wouldn't make sense to require that Li contains no trivial ideals, no ideals, because it always contains these, so this you exclude. So apart from these two, Li contains no ideals, and that constitutes a simple Lie algebra, and every one, L1, L2, up to Ln, finite number of these, are simple. Okay, so we understand this a little better. So every finite dimensional complex Lie algebra can be decomposed as a solvable algebra, semi-direct sum, I'll explain in a second, and a direct sum of lots of, but finitely many, simple Lie algebras. Now let me elaborate a little on the direct sum and the semi-direct sum. So that's C. The direct sum plus between Lie algebras so if I have L1 plus L2, this is meant in the sense of direct sum of a Lie algebra. So if you go back here, I should have maybe written here everywhere direct sum as a Lie algebra and semi-direct sum as a Lie algebra. And so the direct sum between Lie algebras is actually, if you consider this as a pure vector space, it's first of all the standard direct sum between vector spaces, but plus the condition that this separation into two parts is respected by the Lie bracket. That means you take any element from the first vector space and any element from the second vector space, and you take the bracket of these two, and that's of course the bracket in the big algebra L, that be 0. So these two parts don't see each other with respect to the Lie bracket. So that's this direct sum. Okay? And then D, you have the semi-direct sum. Semi-direct sum plus S, well, that can only exist between Lie algebras, because otherwise you wouldn't have enough structure on a vector space to define this. So our example was an L and R, semi-direct with respect to Lie, obviously, and then comes some, say, L1, that shall suffice. Again, as a vector space, this is a Lie algebra, hence in particular a vector space. This is a Lie algebra, hence in particular a vector space. This is the direct sum between vector spaces, no questions asked, plus the additional condition that the bracket of any element of R and any element of L1 in this case, well, won't be 0, that would be a direct sum, that it is in R again, so that R is here an ideal. So that's the semi-direct sum. And so we can now understand, go back to the theorem again. Now we have everything clarified. Every finite dimensional complex Lie algebra decomposes into a semi-direct sum of this part, which is a solvable Lie algebra, and a direct sum of simple Lie algebras. So that's the basic Levy decomposition theorem which we want to use, and there are a number of remarks in order. So the first remark is that it is very hard to classify the solvable algebras. Hard to classify the solvable Lie algebras. Now, so at least there's no classification known. You have to rely on a case-by-case analysis. B is that it is indeed possible to classify the simple Lie algebras, but another remark first. The Lie algebra that has no solvable part, that is, which can be written as a direct sum of Lie algebras that are semi-simple, that are simple. So if each of these are simple, but there is no solvable part, such a Lie algebra is called semi-simple. It's called semi-simple. Okay, and that's something that's very easy to check, as we will see in a second. And remark C is that in these lectures, obviously, so the solvable algebras we can't classify, so let's focus on semi-simple Lie algebras. And obviously, we don't need to classify all semi-simple ones because they, again, decompose into a finite number of Lie algebras that are simple and that don't see each other, because this is the direct product in the Lie algebra sense. So it suffices to study one of these building blocks in order to understand any Lie algebra that decomposes like this. So the simple Lie algebras are the building blocks, are the independent building blocks we will classify. Okay, so that's what we're going to do in these lectures. And there is some preparation needed to do this. So preparation of the classification. So there are actually two technical constructions. So the first one is the so-called adjoint map. So define. So let L bracket be a complex Lie algebra, quite generally, and let small h be some element of L. Then we define the following map. Add h. So this is the name of the map. For each h, you define a new map with name add h. What does the map do? It takes an element in L and it maps it to an element in L in linear fashion. And it's defined as follows. So you take an element small l in L, you map it to add h, acting on L, and the definition of this is simply the commutator, well, the Lie bracket, I should say, not clear whether it's a commutator, it's the Lie bracket of h with L. Or simply, add h is symbolically written h, and the second is an open slot. So add h eats a Lie algebra element and spits out a Lie algebra element. And of course, it does so in linear fashion because, in particular, in the second entry, the Lie bracket is, of course, linear. So that's the adjoint called the adjoint map with respect to the element H in L. That's the adjoint map, and we'll use that quite heavily. So, of course, only again one of these formal tricks where you say I could perfectly well express the commutator. Why do I need to write it like this? Well, it's again one of these formal tricks. Very often it's just convenient to just think of this map rather than to think of this map as it acts on something. That's always the same thing. So that's the adjoint, and we'll look at that in a basis in a second. So, but before we look at the components of the adjoint map in a basis, we'll define, without choosing a basis, yet another object of the utmost importance, and that's the following. So throughout this lecture, L will be a complex Lie algebra, and sometimes, complex Lie algebra. And so now we define the killing form, the bilinear map K, that takes two elements of the Lie algebra and maps them to the complex numbers in following fashion. Well, it's a bilinear map. That K of, well, A and B elements in the Lie algebra is defined as, so what can we do? We can take the adjoint of the element A, that's a linear map from L to L, and we can, of course, compose it with another linear map from L to L, which we choose to be the adjoint of B. So this in total is a linear map from L to L, and of such a linear map, of such an endomorphism on L, we can, of course, take the trace. Okay? And now, because we're on a, well, anyway, this bilinear map is called the killing form. Now, form is a little unfortunate. Well, it refers to bilinear form, which needn't be antisymmetric. So in previous lectures, we defined differential forms, n forms, and they were always antisymmetric. So this form is not supposed to imply that. It's rather going to be a killing, well, it's going to be a symmetric bilinear form. So this, anyway, this is called the killing form. That's a traditional terminology. And immediately we have the remark that because L is a finite dimensional vector space, it follows that the trace I have here is cyclic. You know that the trace only is cyclic over finite dimensional vector spaces. This causes a lot of trouble in quantum mechanics, that this doesn't generalize to infinite dimensional vector spaces. But here the trace is cyclic, and hence the killing form KAB for any AB in the Lie algebra is the same as KBA, so it's symmetric in its entries. So that's the first remark about the killing form. Now, the second remark I wish to make is that if L is semi-simple, or rather we have L is semi-simple if and only if the killing form K is non-degenerate. I think I mentioned this before, but I'll say once again what non-degeneracy means. It means for a bilinear form, if for all A in L, it's true that K of A comma B is 0, that already implies that B was 0. So this is the non-degeneracy of a symmetric bilinear form. And so you see the semi-simplicity that the algebra can be written as a direct sum of simple algebras, or in other words, that it doesn't have a solvable part. That sounds like, and it is actually at first sight, not so easy to determine, but all you have to do is you calculate the killing form of the Lie algebra and you check whether it's non-degenerate. If it's non-degenerate, there is no solvable part. Now this may seem a little abstract at first sight because this at A and at B, there are these maps I defined, but you can actually really calculate this if you go to a basis. So now consider, for actual calculations, the components of add of some h and the killing form. With respect to, with respect to what? Well, this add A is a map on the Lie, from the Lie algebra to the Lie algebra. That means in particular it's a linear map on the underlying vector space, and the K is a bilinear non-degenerate form, if L is semi-simple, on the underlying vector space. So with respect to a basis of this vector space, and we could choose this basis, we could call this basis, well, it doesn't matter, let's call it E1. We're going to use the E1s later. Well, call it capital E1 to capital E dim L, okay? And how does this work? Well, it works as always. If you have such a basis of L, then you can definitely write down a dual basis, epsilon 1 to epsilon dim L, of the finite dimensional dual vector space L star. And then you find the components of a map add of H, but why should we choose an H? We can immediately plug in one of the basis vectors here, so add of EI. That map will have components, let's call them JK, that you get as follows, as epsilon J acting on add of EI acting on EK, because that is how you get the jkth component of an endomorphism. You plug in the EK and you extract this one by the epsilon. Well, it's just this, always this dual construction. It's essentially, it's the definition of components of a tensor. Well, but now we can calculate this. This is epsilon j. Add EI, EK is simply the commutator, EI with EK. All right? And, and now there is an important definition we make. We make it in this derivation here. So this commutator, of course, you take an element from L, you take another element from L, and you calculate the commutator. The result will be an element in L. Well, but L is a vector space, and we've chosen a basis, so certainly this result can be expanded in this basis with coefficients Cm, but of course the coefficient will depend on what vector you plugged in here, which of the basis vectors in this case, and so we should label them by the I and the K of these two basis vectors as well. So it's clear that such coefficients Cm, I, K in the complex numbers exist. This is clear since the result of a bracket is again an element in L. Okay? Hence this is clear. And these guys here, they have an important role if you go to components. They're called the structure constants. They're the structure constants of the Lie algebra, well, with respect to the chosen basis of the underlying vector space. The structure constants. So we can continue our little calculation here. This yields epsilon j of structure constant CMIK EM. Well, here's of course a summation convention at work. But now the epsilon j, they're covectors, the elements in L star. So certainly you can have the constants jump out, and you get C m I k epsilon j of Em. Now, we can choose independent bases E and epsilon, L and L star, but if we choose the dual basis epsilon 1 to epsilon dim L with respect to this basis, which you remember is defined as epsilon j on EI is delta ji, we can always do that, it's uniquely determined, then this is a delta jm, and the result here is C j I k. Okay? So this I from here appears down here in the middle, and the jk appears here and here if you submit to this definition of the structure coefficients. So in fact, the structure coefficients are a very simple thing, a very natural thing to calculate here, and the add of the ith basis vector is nothing, the components jk of that are nothing but this collection of structure coefficients. And that's very useful, and that is why this map abstractly, without having chosen a basis, plays such a big role, because in a sense it represents the structure coefficients, but without having to choose a basis. Now, so that's the add. Now we can look at the killing form in components. So killing form in components. Well, how does that work? Very much the same way as always. I take this bilinear form and I plug in the ith and the jth basis vector, and this defines the ij component of this bilinear form with respect to the chosen basis. That's always the same business. But now let's plug this in. So this is the trace of the add ei circ, so composed with add ej. All of this we take the trace. But we know that if the matrix representation of this guy is C I in the middle, and let's call it J M, okay, that then here it's the J, well, let's call it N first, J L, something like this, okay. Then actually this composition at the level of the maps is mimicked, or it's not mimicked, it's mimicked at the level of the coefficients by doing this contraction here. So it's this matrix multiplication of the representing matrices of the maps. Always remember that these guys just label which map you look at here. And then, of course, the trace at the level of a matrix is just the diagonal, the sum of the diagonal elements. So if J equals K, and no, sorry, J was bad here. Let's call this L, okay, because the J appears here again. So it's then the trace of the diagonal elements. So anyway, this here, I should maybe write this down. So far what we wrote is the components of add EI, circ, add EJ, the L kth component, all right? And now you execute the trace. Well, how do you execute the trace? You execute the trace by setting L to L, so by putting this here. Okay, and that's it. And so the killing form, again, Kij, is C, you write the I here, you write the J here, these are these components, and then there are 4 indices open, and you can only contract in one way. You can contract this one with this one. Well, you could contract in between, but that's not meaningful. And then you have an N, and you have an N. So that's the killing form in components. And this is always very easy to calculate, because this you get directly from calculating all the brackets of your basis elements. And then you calculate this guy, and recall, then you look at this matrix, and if it's non-degenerate, then the killing, you detected that the underlying Lie algebra is already semi-simple. Okay, so I again remark, again, emphasize, because I said it before and now say it in slightly different words, can emphasize L is semi-simple if and only if K is a pseudo inner product. Well, what's a pseudo inner product? It's a bilinear map from the vector space cross vector space into the vector space, and it's a pseudo inner product if it's non-degenerate. Hence, I repeat it again like this. So you just check whether this is a pseudo inner product, and it will have a signature over R. Well, we'll see the signature vanishes, but that's this thing. That's the killing form. And that is, so you consider again, add of some H, some element in L, is a linear map from L to L. Now, quite in general, if you have a linear map and you have a bilinear form, in our case K, from L cross L to L, you can actually decide on whether the linear map is symmetric with respect to an inner product. So recall, a linear map phi, it goes from some vector space into the vector space, is called anti-symmetric or symmetric, right? With respect to, and that's important, you need an, let's say, a non-degenerate inner product with respect to a non-degenerate bilinear form, or the symmetric bilinear form to emphasize this. B, if, by definition, if B of phi of V comma W is the same as B of V comma phi W, that would be symmetric, so that's plus, and the minus here in brackets corresponds to these brackets is antisymmetric if you pick up a minus sign here for all VW in a vector space V. And then here it's simply a fact, and you can check that add H for any H in L is antisymmetric with respect to the killing form. Form K, and you know, for the killing form to be non-degenerate, we require the Lie algebra be semi-simple, and for a simple Lie algebra, in any case, because simple implies semi-simple, and what we want to focus on from now on are these pieces L1 to Ln that are simple, and there we will use this. Okay, so this was our preparation. We met the adjoint map with respect to a picked element from the Lie algebra. We met the Cartan, the killing form, and now we'll find the key definition for the classification, and everything follows from this definition and the following theorem. So if L with this bracket is a Lie algebra, then the Cartan subalgebra, then a Cartan subalgebra, so it's a particular type of subalgebra. Cartan subalgebra traditionally carries the name H for whatever reason, probably because C was already taken by the structure coefficients, structure constants. So then a Cartan subalgebra H is, well, as a subalgebra, it's certainly a vector subspace of the Lie algebra vector space, so vector subspace. Okay. And it correct. It's that, and it's a maximal subalgebra such that, and now this is the key, such that there exists a basis H1 to H sub m of this subalgebra. Well, if it's a subalgebra, it's an algebra in particular. There exists such a basis of H that can be extended to a basis. So extended means I take those base elements of the subalgebra, but I find further ones. Let's call them E1 to E dimension D of the algebra minus m, because we already have m basis vectors, so we only need d minus m further basis vectors, such that, and now it comes, such that the extension vectors E1 to Ed minus m are eigenvectors for any add of H where small h is an element of capital H. Aha! What does this mean in a formula? It means that I can take add of H and I let it act on E alpha, but I can do this for any alpha from 1 to d minus m. I can let it act on any of these d minus m extension vectors that make this to a basis, I should say, to a basis of the whole Lie algebra L. And then I know this must be proportional to E alpha again, because that is what eigenvector means. And there will be a proportionality constant that will, of course, depend on what alpha I look at. The E1 will have another eigenvalue than the E2 and so on. But this eigenvalue will also depend on what H I chose here. Obviously, because for any other H, this is a different map. Right? So that means that this guy here, including the of H, this will be some eigenvector. Okay? And that's it. So this is called a Cartan subalgebra of a Lie algebra. Full stop. If something like this exists. And of course, the big question is, does it always exist? Okay? So theorem says any finite dimensional Lie algebra possesses a Cartan subalgebra. It's the first part of the theorem. That means such a choice can always be made. It's very special, and this is the central equation for the classification. So if there's any theorem to be proven, it's this one. But we're not going to prove it because it's a little involved. Okay? But this is what you want to look up if you don't believe the whole thing. Cartan subalgebra. And the second thing is that if L is simple, then it follows that this Cartan subalgebra is abelian. Which is to say that taking any two elements of H, they commute. So, if For any finite dimensional Lie algebra, something like this exists. And if L is simple, then you also know that these all commute with each other. They are the Cartan subalgebra. They span the Cartan subalgebra. But the H's of those all simultaneously are diagonalized by these guys. Well, the H of all the H's are simultaneously diagonalized by these guys. You're thinking, oh, if they're all simultaneously diagonalized, this is what this thing says, then they better commute. Well, so it's consistent with what you know there. So this is from there. Okay. Right. So now we make an important observation. You might take this as pure notation. You say it's the alpha eigenvalue for a given h. And for another h, it's another eigenvalue. But if you now look at the left-hand side, you have that the left-hand side here is h comma e alpha. And the right-hand side is lambda alpha of h e alpha, right? This is the left-hand side. It's just in fancy language. But it's obvious that this is linear in h, because this is linear in h. It's linear in small h in h. But that means that lambda alpha from h to the complex numbers, if I feed an h into the lambda alpha, if I take triple the h, it will pull out, and as will the 3 pull out here, because it pulled out here. Okay? And if you take the sum, there will be the sum of such lambdas. So that means the lambda alpha, taking this not as pure notation, you can understand the lambda alpha without the h as a map, and as a linear map. Right? So it's a linear map. So it's important whether you write the of h, because then it's a complex number, or you leave it out, then it's a linear map. But that means, or it's the same as, this is also the same as, that lambda alpha is an element of the dual space H star. Okay? Okay. Definition. The lambda 1, 2, lambda d minus m, because there are as many, without, you see, it's valid for any h, but I do not always want to say, and it's valid for any h, so I rather speak of the lambda alphas as linear maps. It's good enough, okay? So lambda 1 to lambda dm, which are all linear maps, so which are all in h star, are called, now this is traditional terminology, but it's good terminology, are called the roots of the Lie algebra. They're called the roots of the Lie algebra. Okay. Now, we also have a name for the set of all rules. Call phi, which is simply the collection of all these roots. Call this the root space, or the root set. I like better root set, because it's really just the set. And you see it's a subset. It's a subset of H star. It's the root set. Okay. Remark or remarks. So again, these are kind of like the eigenvalues, the linear functions defined by the eigenvalues of the H linear maps. And we found that H is anti-symmetric with respect to the killing form. And we're over the complex numbers and so on, from this it follows, after all, that if lambda is a root, so I don't say which one lambda in the root space, if lambda is a root, then it follows that minus lambda is also a root. So the roots come in pairs. If I have a root lambda, then I also have minus lambda. That has to do with the fact that if something, an endomorphism is symmetric with respect to a bilinear form, and this form is symmetric, but it's non-degenerate, it's not necessarily positive. If you think about all these diagonalization theorems, you have that symmetric endomorphisms can be always diagonalized, right? Yeah, if they're symmetric with respect to an inner product. However, this diagonalization theorem is destroyed once the inner product is not positive definite. It makes trouble in relativity, because there you have this only non-degenerate but no longer positive inner product. I've got to be careful, okay? However, because you're over the complex numbers, signature doesn't count, because you always get rid of the signature by making complex basis changes. Signature is only defined for real vector spaces, for bilinear forms on real vector spaces, symmetric ones. Anyway, the whole blah, 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 is we have our complex numbers, anti-symmetric, and so on. After all, I can always find these block diagonal form where I have only minus ones and ones on little boxes on the diagonal, right? And from this you can write this complex as I minus I on the diagonal, and I minus I, and that gives this result. That's the plus I, and that's the minus I, but the I is already maybe absorbed or not. Anyway, that's just a remark. If you have a root, you have always the negative of this is also a root. And the other thing is that the lambda 1, so the set phi, is not linearly independent. It's just a remark, one can show this. It's not linearly independent. However, what we can do, we can find a set of fundamental roots. I give this as a definition. A set of fundamental roots pi, that's how it's called, the set is called capital pi. A set of fundamental roots is a subset of all the roots. So I pick certain roots such that this set now is linearly independent. Why do I talk about linear independence? Well, this is a subset of a vector space, so I can decide linear independence or not. No? But now I take a subset of this set such that it's linearly independent, and the property B is such that every lambda, every root that I found, for any such root, there exist integer numbers n1 up to n. Yeah, okay, now we have to probably say, if this is a finite set, as we saw, then this is a finite set. So we can name the elements of this finite subset, let's say down to little r or little f, like number of fundamental roots. Then you have numbers n1 to nf from the integers. Okay, so it's a definition. You look for such a set of fundamental roots, such that any root you have in the phi can be written as plus or minus, but you have to decide once and for all. Well, you have to decide for every lambda, you have to decide. Okay, so I to be mathematically clear, should there exist such guys, and there exists an epsilon that's either +1 or -1, but for every lambda you could choose a new one, such that lambda can be written epsilon times the sum I equals 1 to f of these integer numbers, and they can be zeros, of these non-negative numbers, ni pi I. Okay. It's very simple. You get these eigenvalues from the Cartan subalgebra, these roots, these maps. But you want to only pick a subset of these guys, so they get a special name, they're called fundamental roots, such that they're, first of all, the subset is linearly independent, whereas this was not linearly independent. And secondly, you also demand that you can generate every of the guys in phi from this subset, but by only using non-negative numbers. Well, that would already prevent you from, if you chose a root, would prevent you to choosing the negative root, which we know is always also a root. Okay, but these two are certainly linearly dependent, this lambda and the minus lambda. So I can only choose, of any pair of roots, I can only choose one of them so that I don't destroy this. But if I had this, I must be able to produce the minus sign. Well, I will not be able to produce the minus sign if I only have non-negative integers. But then I need an overall sign that takes me to the negative. That's something different than requiring that these guys are from Z, because then the first coefficient could be positive and the second coefficient could be negative. That's not allowed. They're either all positive or all negative, because the epsilon moves in there. Okay, so this is this set of fundamental roots, and the fact is, can always be found. Such pi in phi can always be found. Okay, theorem. In particular, if I take only these fundamental roots, and I now don't only take these funny integer coefficients, but I take any complex coefficient, and I look at the span of this. So I look at all complex linear combinations of this. What I will get is I will get the dual of the Cartan subalgebra. So you see, the lambdas, they were a subset in the dual of the Cartan subalgebra. But they were not a basis of the Cartan subalgebra because they were not linearly independent. But they have a very important role, and so I need to know all these roots. But there's redundant information in there. I only choose a basis from these roots, and they already span this entire guy. Okay, so this is to be kept in mind. Yeah, that's this thing. They span this. So that's the set of fundamental rules. And an important remark is, as usual with finding a basis, pi is not unique. It means two different mathematicians may choose two different sets of fundamental roots, but they're always to be chosen from the root space, from the entire root space. Okay, so we need some more machinery. So we need more machinery, and unfortunately this is the case, but if you then follow the argument further on, you'll see that it's very natural machinery. Maybe seem a little ad hoc first, but the first thing we now define is we define a space with the fancy name HR star. Okay, now what can this possibly be? Well, we had the H star, and that was the span over the complex numbers of the spaces. And now I decide to take these fundamental roots, but to not take complex linear combinations, which would give me the whole H star, but you guessed it, I only take real linear combinations. Okay, so this kind of leads to so that's the definition, and that will be a very useful space to look at. Okay, thus we have, so let me, we have this root space pi, and that's a subset, the fundamental roots are a subset of all the roots. And these guys here, they are spanned, so I write here an equal sign in quotation marks, okay? They're in a sense this funny span of the integers, but with this overall plus or minus sign that we had of the pi. So we have this fundamental root space, and if we take these integer linear combinations, but with an overall sign, then we get back all the roots. I remind you, the roots were just the functions, the linear the functionals that came from the eigenvalues of the adjoint map. Okay. Now, certainly this is a special case of taking real coefficients without any overall sign. So this clearly is a subset in span R of pi. It's a subset in HR star. So this is now the span, well, these quotation marks, this thing here is funny, but you know what I mean. It's the final form, span R of the pi. And this clearly, again, is a subset in the complex span of the pi. Okay, so we're dealing with all these different ways. This is what we originally came from, because we have complex Lie algebras. We now decided we're also interested in this guy. This guy came up from the Cartan decomposition, and these pi's from the need to find a basis for this guy or for this guy. This is the fundamental roots. So all these three ways of combining the fundamental roots play a role. That's what it is. Okay. I think if one writes it down like this, one can keep track of the various things one looks at here. So that's the first definition. And the second definition is we want to look at the killing form, but not on L. So we already have a killing form that takes two elements of L and maps them to an element of L. What we can certainly do, we can look at the killing form, but the killing form restricted to H. Well, that's a simple thing. That is just a bilinear map from H to H, because H is a subalgebra of L, the Cartan subalgebra. I can just choose to only plug into the K elements from H. I'm sorry, this is not right. This is like this, goes into the complex numbers. I'm sorry, it's a killing form, goes to the complex numbers. And I can certainly restrict this to the H by just plugging in these guys for H. It's a restriction of the killing form. But I now want something different. What I want is I want to take a dual of the killing form that is restricted to the dual of H. Well, that's a complicated object, so we're not going to call it like this. We're just going to call it K star. We want a K star which takes you from two copies of the dual into the complex numbers. Well, you know this. If you have an inner product on vectors, it induces an inner product on the covectors. If this is non-degenerate, because if it's non-degenerate, you can find the matrix inverse as the coefficients. Okay. And if you want to define this guy, you have to say K star of, so in H star, what lies there? I don't know, let's say in the lambdas we already used, there lie mu's and nu's. So we have a mu and we have a nu in H star. And of course, we want to reduce this to the killing form on L, or the restricted one. And then I need to use this canonical isomorphism I, that takes me from H to H star, okay? And I can do this by, so I define this in between, this is in a little cloud, by saying I of a little h is given as the killing form of H comma open slot. Because obviously this is I can linearly put in another element from H here, and I get a complex number. That means this guy is an element of H star. I take this here, but then I use its inverse. I have to show that, but this has an inverse if the K is non-degenerate. So the inverse exists. So think again. I inverse exists if the K is non-degenerate, if L is semi-simple. And semi-simple, simple is enough. Okay? And we have a simple Lie algebra, so we have the inverse. You can think about this. And then I take the inverse mu, I inverse mu, and I define this dual killing form. Again, it looks terrible. It's just if the killing form has the indices k down ij, this guy has the indices k up ij, and k up ij with k down jk is delta ik. It's as always. It's as always, but this is the coordinate-free version. Think about this. Okay, so we have the dual killing form on this dual space H star. Now, theorem, if I take this dual killing form and look only at H star over R, so I restrict it further to only act on these guys, then it lands in the real numbers, first of all. It's bilinear and lands in the real numbers. And it's positive definite. So K star of any, I don't know how to call them, alpha comma beta, where alpha and beta are from H star R, so only from these real linear combinations, or alpha alpha, sorry, is greater or equal to 0 and equal to 0 if and only if alpha is already the 0 in H star R. Which is remarkable because before we only knew that on the complex vector space this killing form is non-degenerate. But now we found a restriction to real vector space where this becomes a real inner product. Okay. That means that on H star R, which again was the span of the fundamental roots over R, we can calculate lengths and angles. In particular, and that's the reason why one constructs this, in particular, one can calculate the length and the angle, or the length of and the angle between fundamental roots. Fundamental roots. Because they span it, so I can certainly calculate the length and the angles between basis vectors I found. But all the roots, they're a subspace of this span R pi, hence I can calculate lengths and angles between any roots. Okay? But we'll actually, so I take away the bracket again, but we'll actually need it to calculate on the fundamental roots. Okay. So we're slowly coming to completion. Now, there's one more thing we need, and that's the so-called Weil group. The motivation is the following. Again, we chose the pi such that it spans the Cartan subalgebra over the complex numbers, all right, and that it's a subset of the phi. That's fine, but once you have chosen a subset, you might worry how if I have only this information, you can span this whole guy, but can you recover any of the other elements in this set of roots? Remember, the set of roots is important. It came from the Cartan decomposition. Can you recover every guy in here purely starting with this information? The answer is yes. And the whole classification of Lie algebras comes from understanding the fundamental roots of the algebra. So everything about the Lie algebra doesn't matter. The only thing that matters is this pi. And you see, this is not even the whole Lie, this is only the dual of the Cartan subalgebra. But the whole big L, if it's simple, you understand if you understand this little guy. So we recover everything here, but can I, now I know, okay, I can span all the phi's with this funny overall sign and then non-negative integer linear combinations. But you see, by taking this entire, aha, you see this was wrong, and I knew why this is only, of course, a subset of this. I can span by this, I can span much more than this. The condition was choose these such that you can span every guy in here, but the entire span is bigger than only this. Okay. So the worry is, can I, with this information, recover precisely the guys that sit here? And the answer is yes, but that works as follows. So, question, how does one recover precisely the set phi, from a given set pi of fundamental roots? How do I recover all the roots from the fundamental roots? And the key is in the following definition. For any lambda in phi, although in a second we're only going to use it for lambdas in pi, but we define it like this. For lambda, every lambda in phi, we define the map S sub lambda, which takes an element in H star R and maps it linearly to an element in H star R. And it's defined as follows: as lambda acts on some mu, which lies in H star R, as follows: it takes the mu, that's certainly linear, and then it subtracts 2 times, and this expression you might recognize, lambda comma mu by lambda lambda times lambda. Takes this ray. Okay. So anyway, this is the definition. You can check this is linear in mu because linear here. There's 1 mu in here, sits in a slot of a bilinear map. So that's linear in mu. But it's called, of course, highly nonlinear in lambda. You might say, well, yeah, well, it's highly nonlinear in lambda because, for instance, if you scale lambda, the scale vanishes because an alpha pulls out here, an alpha here, an alpha here. It's alpha by alpha squared, but there's another alpha. The scale vanishes. Right? So by real rescalings, because this is only a real vector space. In quantum mechanics, you look at objects like this and you want complex rescalings. This is the ray, this is the state of the space. Anyway, so this is the same construction here. So I put up a warning sign. Yeah, linear in mu, certainly nonlinear in lambda. And anyway, this thing we defined and is called the a Weil transformation. So any such S sub lambda is called a Weil transformation. And it acts on this real version of the dual of the Cartan algebra. And if you take W and you take all these S lambdas together for any lambda in the root space, this is called the Weil group. It's called the Weil group with the group operation being, well, what can be the group operation? These are maps, the composition of maps. Okay, this is the while group. So now we have an important theorem about the while group, namely a theorem that relates the fundamental roots to the entire while group. So the first statement here is that, I first give it in language terms, the while group is generated, I'll say in a second what that means, is generated by the fundamental roots. So in the roots in pi, okay? And so the remarkable thing is that the fundamental roots suffice in order to generate the while group. Now what do I mean by it's generated? I mean that, that's the explanation, that for every element small w in the while group, there actually exists a finite collection of pi 1 to pi n. It's just a selection of pi's in pi such that the w can be written as a composition as pi 1 circ as pi 2 circ ... finite as pi n. So this is the group operation, the circ, and you can generate every element in there by only taking the s down some fundamental root. That's the first statement. The second statement, very important, is that every root can be reached from a fundamental root by an action of an element of the while group. So every root, well, let's call it lambda in the root space, which is not only the fundamental roots, it's every root can be reached, or produced, let's say produced, can be produced from a fundamental root, let's call it small pi in capital Pi, so that's the set of fundamental roots. This is a particular one from a fundamental root pi in pi by action of some element of the while group. So let's say by action of the while group. So that means that for every lambda in the set of roots, there exists a w in the while group and a small pi in the set of all fundamental roots, such that the lambda is simply the s sub the w, well, w can take the form of some s something according to here, of some w acting on pi. That's it. So if you know the fundamental roots, you already know the entire while group. But even more, if you know the fundamental roots, you then also know every root, because it can be generated by the while group, which comes from the fundamental roots, generated by the fundamental roots. So the fundamental roots in this two-step process determine the entire set of roots. That's why they're so important, and that's why the while group is so important. And now the final question is, what happens if the while group doesn't act on a fundamental root, but it acts on a general root? Well, the while group merely permutes the roots. What does that mean? It means that if you take the while group, so for every element w in the while group, it's true that for all lambda in the set of roots, the action of the element of the while group on lambda lies again in the set of roots. That means the Weil transformations, which actually could take you out, I mean, they act on all of H star, they could actually take you out of the phi, but they don't. They simply permute the groups. And these three properties are very important for the following.
The inner product and the definition of the Weil transformation, that just comes from the sort of dual killing form.
I am sorry. Yeah, very good. Thank you very much. This is the dual killing form in both places. Thank you. Very important. Didn't use it anywhere else. Yeah, that's right. Okay, it's from the dual killing form because that can eat these guys. Good. Yeah, thanks for the remark. So, now, showdown. Okay, so what do we do now? Well, we tie together all the information we have. Consider the following expression. We take the Weil transformation of one element from the fundamental roots acting on another element of the fundamental roots. So for the ith and for the jth element in the fundamental roots, we look at this guy. We talked about it before, but now we write out its definition. So by definition of this Weil transformation, this is the pi j, needs to be linear in a second slot, minus 2 times, as was just remarked, the dual killing form of the pi I by the dual killing form of the pi I, comma the pi I. And there's the pi j once in here, because it's linear in pi j, and these are just the coefficients if I have here the pi I. So this is the application to the fundamental roots. Now, I know that if I have these two guys, I know that the result lies in the root space, because that is what I just claimed. I said you do this for any two and you're guaranteed to exactly reproduce the root space. So I know this from the previous theorem. Okay? But what do we know? You see, this is an expansion of a root in terms of two fundamental roots. But what do we know about the roots being expanded in terms of two fundamental roots? I know there is an epsilon and there are coefficients ni, so that I can do this. So there exist ni's in the non-negative integers, such that I can write any element. Well, okay, this is the span. Oh dear. Set. Any guy in here can be written like this. Aha! That means in particular, this guy must be of this form. You say, sure, factor 1, and there's another integer factor. No, not integer factor. If this is a factor 1, then I write this as plus, that's the sum sign, minus 2 times, that's a number, minus 2 times this guy. But if these are fundamental roots, and they are, then this coefficient must have the same sign as this coefficient. Is that right? Because if a coefficient that's non-zero appears, it has the same sign as the other coefficient. Hence, we know that this whole guy must be in N, Okay, so that's important. That is, if I leave out the minus sign, then I know that I use the 2. I know that 2 times k star of pi I comma pi j divided by k star of pi I. So you should be very careful. This is a j. This is pi j only once in this expression. I know that this is some negative integer. What about 0? No, some non-positive integer. Non-positive integer, because this could be 0, and then if I leave out the minus sign, it becomes from non-negative, it becomes non-positive. This is a non-positive integer, and these guys are so important, they get a name, and they're called C. Now this is not the structure coefficient C, this is a new C. C that has two indices, namely I, J. And now I ask you, is the Cij symmetric? What do you say? So is Cij the same as Cji? Yes. No. That's what I thought this morning at 4 o'clock. I thought, darn, I mean, it's symmetric. It mustn't be. It's not symmetric because, look, the j appears in there once and the pi I appears there 3 times. Only the numerator, it's symmetric because the killing form is symmetric. But if I replace I by j, I have to write the jj here that may have another length. And it fails to be symmetric. So, not so early this morning, I thought the same. Okay, so exclamation mark, Cij not symmetric. Don't only look at the numerator, look at the whole expression. It's not symmetric, and it's called the Cartan matrix. Cartan matrix. And we, of course, also know, clear, that if you look at Cii, that will always be 2. So the Cartan matrix has on the diagonal, it has 2s, 2, 2, 2, 2, 2, and on the off diagonal is some non-positive integer. That's the Cartan matrix. Now, define the following matrix, Nij, and that's defined as Cij, Cji. You know this is not Cij squared, so no sum. There are no sums taken. No summation convention. I take the Cij and I take the object if I exchange the I and j, but it's not the same object. It could be another number, yeah?
So is that not a contradiction to your some non-positive integer 2 is positive? Then your whole box, you cannot say that this is always non-positive.
Ah. Okay, hang on. What's the business here? Cij is 2. I'm confused. Oops. No, that's not good. Okay, let's think again. So I think we arrived here, and that was right because that came from the while group. Now I have a positive factor here, so this whole thing needs to be non-negative. It needs to be, well, roughly speaking, needs to lie in n. Now I take the minus sign away. No, you're right, this cannot be. Huh? Thank you for this. This looks silly.
Perhaps you want the minus sign before the first pi j. I don't know. You can.
Yeah, but you see, my problem is if I put Cii, then I have pi I by pi I, that's 1. The result is a 2. Yeah, it simply doesn't work. But on the other hand, from here, I have this minus sign, because this is the while group, and the while group needs this minus sign. So it's really pi j minus this other thing, because otherwise, so that I check. So you need the minus sign here. I'm puzzled. I'm really puzzled.
But
yeah?
Isn't k star, if you plug in pi I, mustn't this be 0 because k star is anti-symmetric? And then you have
No, k star is symmetric. K star is the induced bilinear, as is in the sense the non-degenerate metric. or even the positive definite metric. No, this is symmetric. This is symmetric. No, I'm thinking about something else. Aha. Maybe I can make this conclusion nur for I non-equal j, because if I equals j, these two, aha, very good, thank you for the remark. This conclusion is only true, this here is only true for I not equal j, and this is also true for I not equal j. Why? Because I have this expansion, but if I equals j, then these two factors, they combine into something positive or negative, but that perfectly fits this definition because there's only one factor. That was my mistake. So thank you very much for the remark. So this needs to be restricted to this, and then everything is fine, and this is nevertheless still true. This is true, so you make this definition, so that's the thing. You make this definition for any combination ij, for any ij, but it's some non-positive integer only for I non-equal to j, as we read off from here. And for I equals j, I have to discuss anew, but then I don't get a constraint. I only get the constraint, it's an integer, but then I immediately learn it has something to do. No, but hang on, but then it's then it should be -1. Okay, I'm puzzled. I hope I will be saved by the bell. Okay, let me think about this again. I'm pretty sure that the Cartan matrix has the 2 on the diagonal. No, it has the 2 on the diagonal. There we are. I define this for any ij. It's correct. For any ij, I said I to j, then I get the 2. That's fine. This is the Cartan matrix, and I know that on the off diagonal is some non-positive integer. That's all I want to say. No, it's fine. It's fine. There's no contradiction anywhere. Okay, but thanks for this remark. Now, I define these guys, and I could call it the bond number. So small bond is the bond number. And what does it mean? Well, let's write down what it is. What is the Cij? It's 2 times, and another 2 times, it's 4 times k star of the pi I pi j divided by the k star of the pi I, but then times k star, now opposite order, pi j pi I, so the j is in front, the j is here in the back, but now it's divided by k star pi j. Okay? It's this guy, and what is it? It's 4 times the cosine squared of the angle between the ith and the jth root. Isn't it? Because this is the cosine squared. Anyway, that's what it is. It's the cosine squared of the angle between the 2 roots. And because it's the cosine squared, we know that 0 is less or equal to nij, is less or equal to 4, because the cosine squared only takes values from 0 including to 1 including. So the factor of 4 produces this. Okay? So this is for all ij. For all ij. So you find that 0 is less or equal to the bond number between 2 roots less than 4 if I is non-j. You can think about this. Okay, and you also know the bond number is the product between 2, for I non-j, is it the product between 2 non-positive integers. So this thing here is the product Cij, Cgi, and these are non-positive integers. And the product must be less than 4. That is, nij can take the values 0, 1, 2, 3. Because the product of 2, well, anyway, that's this. But in what ways can it do that? So I can have Cij and Cji, and this can result in an Nij, which is the product of the two. Well, first case, n is 0, that happens if this is 0, but if this is 0, then also this is 0. There is no other way to realize this. Then you have, and you can think about that, and then you have an Nij here. This essentially because of the that this can only be zeros at the same time because of the of the positive definiteness of the killing form. Anyway, now you have the Nij that you can only get by having a minus here and a minus here. That's the only way by which a product can yield you the 1 from the way it's defined. But now it becomes interesting. You have the cases 2 and 3. And here you have two choices. Either Ij is minus 1 and Ji is minus 2, or the other way you can generate this 2 is having here the minus 2 and there the minus 1. And the same is true down here for the 3, bond number 3. You can have a minus 1 and a minus 3, or a minus 3 and a minus 1. Okay. Okay, but if you have this situation, so let's look at this situation, then you can derive, that's a two-liner, I leave that to you. You can leave that the pi I is then either less than the pi j, so the length of one of the roots of the ith root is less than the root of the length of the jth root, or it's exactly the other way around. This is all you get from the Cartan matrix, and now you can write down the Dynkin diagrams. The first rule is for every fundamental root, draw a circle. Okay? The second rule is if these two circles represent pi I and pi j from the set of fundamental roots, draw Nij lines between them. So e.g., two lines. But what can you draw? You can draw no lines. That's the case n equals 0. You can draw one line. You can draw two lines. Or you can draw three lines. And that's all you can do, because the n only runs over that range. And the third is if there are two or three lines between two roots. So if we're in this case or we're in that case, then you know that goes into two subcases. Use a less than sign to relate the roots. So for instance, you can have two lines between the roots, but then can be two cases. It can be that one root is less than the other root or the other way around, and we put the relation sign over here. It's like an arrow, but that means the length of this root is bigger than the length of that root. Theorem, and that's by Killing and independently by Cartan, says any finite dimensional simple C Lie algebra can be reconstructed from its set of fundamental roots set capital Pi of fundamental roots, and the latter only come in the following forms. So now we go. There is a series AL. Well, yeah, the series is called A, and this is a root space. That's one possibility. Then you can have this root space, fundamental root space. You can have this one, and so on. So you can add more and more to this ad infinitum, and you call this the space A1. This you call, or the diagram A1 is called A2, this you call A3. And so you have a series AL for L greater or equal to 1. Any such diagram is a Lie algebra of the series AL. The series BL starts with 2, and it has a double line. And now you could imagine a whole number of things that happen, but in fact the only thing that happens is you can have an arbitrary number of single lines, and only at the end there's one double line, and so on. But at the end you have the double line, and so on. And these are called the spaces BL, and they only start at L greater or equals to 2, because the L1 would be the same as this one. And for instance, you never have a space where you have the double line here, or double. It simply doesn't exist. That's not a Lie algebra. And you can actually prove this. That's this thing. But now we have the double line. We have to say how the bond goes. And what's the convention? I keep forgetting. The standard convention is that the bond goes out. Chick, 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 chick. Now, obviously, you can have also the possibility where the bond goes the opposite direction. But if I start with 2, that's the same diagram because of symmetry. But as soon as I have one line like this, this is a different diagram. And so on. And that's the so-called C series. And it starts at L greater or equal to 3. And then finally, there's the D series. And that starts at L equals to or greater than 4. Well, I anyway start here. That's 1, 2, 3, 4. That diagram looks like this. And then the next in the series is this one. The next in the series is this one, and so on. That's this series. And these guys are called the 4 classical Lie algebra series. Well, it's actually sequences, but they're called the series. And then there are 5 exceptional Lie algebras, and they look like this. 1, 2, 3, 4, 5, 6, and this guy is called E6. But there's no series. They don't go on. Well, it goes on a little. Then there is E7, 4, 5, 6, and you have here this guy. This is E7, and you also have E8. 1, 2, 3, 4, 5, 6, 7, 8. That's called E8. So some people try to base physics entirely on the E8 group. And then there are 2 more. One is called F4. That guy looks, yeah, exactly like this. Then there's a double line with an orientation, but that's F4. Obviously, you can do the orientation in the opposite direction, but it's the same diagram. And then finally, there's a diagram, the only diagram with G3 bonds. That's called G2. And that also has a direction, but it's also the same as the diagram with the other direction. 4 infinite series, and 1, 2, 3, 4, 5 so-called exceptional Lie algebras. They're all Lie algebras in the same right. These are all the fundamental root spaces the number of lines between them tells you what the angle between the roots is, if you think about it, because the bond number had something to do with the cosine squared between them, okay? And the arrow has to do with the relative sizes of the roots. That means here all the roots have the same size, okay? Only if you have double or triple bond will the sizes jump, okay? And because these diagrams are all, each one is a connected diagram, each one stands for a simple Lie algebra, but these are all the simple Lie algebras. There is no other Lie algebra. So for instance, is not a simple Lie algebra. Okay? For instance, you could have thought so, you can write down the root spaces, but it doesn't correspond to a simple Lie algebra. And these are all of them. And that's the final result, and these guys are called Dynkin diagrams. And once I give you such a diagram, and I will do so on the problem sheet, I will move you through it. On the problem sheet, I will give you, and maybe we'll do it in the, okay, anyway. I will give you the diagram, and from the diagram, you will reconstruct the root space, and from the root space, you reconstruct the entire Lie algebra. So an exam question could be, write down the root space for G2, or write down the Lie algebra for A3, or for D1, 2, 3, 4, 5, for D5. Okay? Well, I probably won't ask it in the exam, but it's something you can do, and so these diagrams are all the Lie algebras. You can construct from them. And that's cool, right? I hope. Okay, thank you.